Thank you very much. I'm really very grateful for this opportunity to talk about what I consider probably one of the most interesting topics in chemistry ever, which is observing single molecules. Observing single molecules and getting to know their behavior. The results I will present have been obtained in cooperation with several groups, in particular with the group of Takashi Kumagai, Ronhard Grill in Berlin and Graz, Freddy Meixner in Tübingen, and actually we cooperate with Warsaw physicists, not on single molecule spectroscopy, but many of the single molecule experiments have actually been inspired by our cooperation. I will start with these two pictures, which always makes me wonder. Actually, I get into some kind of a philosophical mood when I look at these two. So the picture on the left is, of course, the starry sky. And the picture on the right are single molecules, and these pictures look exactly the same, and actually even dynamically they are the same, because the single molecules that communicate with us by emitting light, they also blink like stars. And if you compare the size of these two pictures, you sort of ponder how interesting is our world and how similar are certain things that are considered to be completely different. When you consider the number of stars in our galactic or in the universe and the number of molecules in a typical probe, again, this is quite sometimes this gets quite similar. Anyway, only 30 years ago, when someone mentioned in our seminar that you know what, I just came from a conference and this guy, Michel Horry, was talking about single molecules. Well, some people reacted quite skeptically, I should say, and they didn't believe that such an endeavor is possible. And nowadays, it's more or less routine, at least in many laboratories, and people learned how to look at single molecules using different techniques. In this talk, I will start by telling you why actually it is interesting and novel to study single molecules. Then, of course, I will say a few words how to do this. And then I will give you some examples of applications relating to tautomerism, which is our main hobby, but also to a very general subject of photostability and heterogeneity in the environment of single molecules. So let us start. Why are we doing this? Well, I think the main advantage of looking at single molecule is to avoid averaging. This simple example shows you that if you have objects oriented vertically and horizontally with the same probability, and then if you do the averaging, of course you will get the average value of 45 degrees. And actually, this value of 45 degrees can be obtained by an infinite number of distributions. We know nothing about the distribution, we just have this average number. Whereas looking at this object one by one is the only way of giving you the exact answer, what is the distribution. So avoiding averaging is actually the main advantage of single molecule spectroscopy. Although it doesn't mean that it's sufficient to look at a single molecule in order to get some important conclusions. You need to
of course, in the statistical description, there are higher moments or higher correlation functions that can bring the same information.
Well, not exactly. Usually, the experiment only gives you the access to the lowest moments, and then you can do more and more. But until you know them all, it's not possible to get it. At least from the practical point of view.
There are also interactions, right?
Yeah. Anyway, this is the main advantage. I think that this is the sort of PR for physicists. When it comes to chemists, a single molecule is, of course, the ultimate detection limit in analytical chemistry. So if you can really detect a single molecule, you cannot do any better than that. Here, actually, the real problem, at least nowadays, is not to detect a single molecule, because this can be to observe a single molecule, because this is more or less routine, but to find it. For instance, in 1 milliliter of blood, if you want to find a single bacterium in a droplet of blood, you have to be very smart in order to really pinpoint it. It's more or less like looking for a needle in a haystack. Anyway, this is kind of PR, but how to do this practically? How to observe a single molecule? Well, of course, this single object of studies has to be separated from the environment in a way. And the separation can be of various sorts. You may, of course, do it spectrally. Actually, this is how it started. It started by studying single molecules at very low temperatures. And then under such conditions, these single chromophores were quite well separated from each other spectrally. So it was possible to excite a fluorescence of a single molecule by tuning the laser, as exciting a sort of not at the maximum of the distribution, but sideways. And this was, of course, nice and practical, but the real challenge was to do this at room temperature and under conditions where the spectral separation was not possible. And for this, of course, you need to separate these single molecules spatially. Usually for fluorescence studies, we do this by just placing a molecule in a polymer, so it cannot escape, it cannot move, so it is fixed in space. And of course, it should be spatially separated from other molecules by, say, a few microns at least. You can also do this in a slightly different way, which is temporal separation of a single molecule. Actually, in this technique, which is the basis for fluorescence correlation spectroscopy, you just focus a laser beam onto a very, very, very small volume and wait until a molecule arrives and leaves. Actually, this is also a way of determining the diffusion coefficient. Anyway, these three techniques are of course complementary, and I think that the spatial separation is the most popular one nowadays. At least what I will be showing you deals mostly with the spatial separation. So we are actually studying our single molecules using three different techniques: confocal fluorescence microscopy. Then we also do Raman of single molecules. This Raman signal has to be enhanced in some way. So we usually put our molecules in some kind of plasmonic environment. We also use resonance Raman excitation, but anyway, it is possible to also obtain the spectra of Raman spectra of single molecules. And a completely different approach is to do microscopy, but not optical microscopy, but scanning, tunneling, or atomic force microscopy. And this we do not do in Warsaw, but we cooperate with people in Berlin and in Graz using our favorite molecules, porphyrin isomers. There are actually quite important differences between studying normal fluorescence, bulk fluorescence, ensemble fluorescence, in which case what people usually do is registering spectra, and by using time resolved spectroscopy, registering the fluorescence decays. In single molecule fluorescence, usually the photon budget is quite limited. There is not enough photons, so we usually actually do not separate these photons spectrally. We collect photons across the whole fluorescence spectrum, and we record time traces. So time trace is just a history of how the molecule, a single molecule, is emitting over time. And you can see that this emission is actually fluctuating, sometimes very strongly, as here, sometimes less strongly. But anyway, this is not constant. Of course, there are fluctuations in single molecule emission, and the analysis of this fluctuation tells us about what the molecule is really doing after excitation. And what is also important is that such time traces usually tell us that we are really dealing with a single molecule. Why? Because this time traces end abruptly. the molecule dies. Actually, this is not exactly death, because the molecule can actually after a while be emissive again. But at least for a moment, we say that this kind of behavior, abrupt stop of fluorescence, is a very good argument for claiming that what we are observing are really single molecules. And then, of course, there's imaging, raster scanning of a sample, and then we see an image. We see an image, and this image corresponds to a single molecule, and actually we see various patterns of these images. I will later explain you what this means. There are quite important differences between single molecule and ensemble fluorescence. First regards photostability. I'm not saying that the photostability of a single molecule is different than the photostability of a molecule when it is investigated together with others. But consider the following situation. If you have a typical sample solution, say 5 milliliters or 3 milliliters in a 1 centimeter cell, and then you measure fluorescence using the ordinary conditions, it can be estimated that on average, one molecule absorbs a photon once in a second. And so if the photodegradation quantum yield is, say, 10 to minus 6, which is a good result, it means that such a solution will start decreasing its population in about 2 weeks. Whereas if you have a single molecule, of course, it's sort of immersed in the ocean of photons, and it can absorb even millions of photons per second, which means that this molecule will be living under single molecule detection conditions for a fraction of a second, sometimes for a few seconds only. So that's a big problem, and this problem has to be treated somehow. Then there's spectral diffusion observed in single molecule emission. Sometimes the emission really fluctuates not only with regard to intensity, but with regard to the spectral characteristics. As the environment evolves, so does the emission. And the spectral diffusion actually is a subject of various studies. It's really telling us quite a lot about what's happening in the environment of a single molecule. A single molecule is a very good probe of the environment, as opposed to the ensemble of molecules in which we average all these interactions. But I think the most important thing when it comes to the difference between normal and single molecule fluorescence is the definition of brightness. Brightness is usually defined as the product of the absorption coefficient and fluorescence quantum yield. And this is not correct for single molecule. Why? Well, brightness should translate into the number of photons emitted per second. And if you have this ensemble of molecules, so if a single molecule, if any molecule absorbs on the average 1 photon per second, we do not care what happens after 1 second. Everything returns to normal, so to speak. Whereas a single molecule, after absorption of a photon, can, of course, go, for instance, into the triplet state, and this triplet state can live for microseconds or milliseconds. And for this period, the molecule is sort of out of the game, so it doesn't emit. So the molecule has these dark periods, and these dark periods lead to, of course, the decreased number of photons emitted per second. So this definition of brightness, which is correct for ensemble studies, is completely wrong when it comes to single molecules. And actually, this is still a question of, well, it's a misconception shared by even people who did quite a lot of fluorescence studies under normal conditions. They sort of cannot believe that a molecule which for instance has a very small fluorescence quantum yield, but very small population of triplet, it can be much brighter than the molecule which has a very large quantum yield, but at the same time, high probability of achieving the triplet state. As I said, the photostability is an extremely important factor. Photostability actually is what determines whether our molecule is good for practical applications or not. And we are trying actually to understand the mechanism for photodegradation of organic chromophores by looking at them and then trying to develop procedures that can be used for controlling and perhaps also improving photostability. People normally, fluorescence is used as a major technique by biologists, even medical doctors. And of course, they want to see something. They want to see something, usually some biological objects like tissues, for instance. And after, say, 30 seconds of irradiation, the image disappears here. So what they are offered are some kind of cocktails that apparently prolong the observation period. But there are many problems with that. For instance, this one, anti-fade kit is for non-living specimen only. It should be used, the mounting medium and the mixture should be used as soon as possible, and so on and so forth. And this is, I think, well, of course this helps, but it doesn't solve any problems related to photostability. So let's say, what kind of strategies do we have to enhance photostability in the presence of air? Carefully select the environment. This is the strategy number one. And I would like to show you some single molecule spectra, actually time traces of the same molecule. This is a kind of a standard, a gold standard for single molecule studies, a molecule that has been studied from the very beginning. It has a strong fluorescence, and it's also very photostable. It's very photostable, but we found that doing these experiments, fluorescence experiments in various polymers leads to huge differences. So we can have the photobleaching quantum yield that varies over 2 orders of magnitude, depending on the environment. It's always a polymer, but these are different polymers. And if you look at time traces of this molecule embedded in different polymers, you will immediately see differences, right? For instance, in polyvinyl carbazole, this time trace, this intensity is very stable. Here it's somehow changing. In polycarbonate, it's blinking like hell. And what does this tell us? Well, it tells us that there's some kind of factor or factors that really influence the photostability. And by comparing these results with the known properties of the polymer, we actually concluded that what is important is not whether we have oxygen or not. Actually, this photostability is not correlated with oxygen solubility, but it's really correlated with the diffusion coefficient inside a polymer and with permeability. And because of that, polyvinyl chloride is the most photostable environment, so to speak. Actually, when I was showing this to some people in the US, I found out that until early 60s, polyvinyl chloride has been used in the US as a polymer for wrapping your sandwiches. And then it was banned because it contains some byproducts which may be harmful for your health. But regarding oxygen, people knew it already in the 50s, that if you really want to avoid the diffusion of oxygen into your sample, you should use PVC if you are not afraid of dying from cancer because of these additives. Another strategy is actually completely different. Now we are interested in photostability, but we do not care about emission. So we are losing the possibility of seeing fluorescence, but in exchange we have a possibility to observe Raman spectra. We put our molecule in a kind of a plasmonic environment. Gold, silver nanoparticles touching each other, creating these hotspots. And in such way, we are actually killing or drastically shortening the lifetime of excited states. And under these conditions, all these photochemical channels which are responsible for photodestruction are of course reduced. As I say, we lose something, but we found that by using such procedures, we can enhance the photostability at least by 2 orders of magnitude. Well, another strategy. Usually, when a molecule is decomposed after absorbing light, it's due to the triplet state. It's because the triplet is usually much more long-lived than the singlet. And so if we can bypass the triplet, if we can really alter the photophysics of a molecule in some way, we may expect to enhance the photostability. And we actually checked that using a series of molecules, which we have been studying for years. These molecules form complexes with alcohols or water. And upon formation of these complexes, photophysics is changing in such a way that there is a very high probability of internal conversion from the excited singlet state directly to the ground state. And in such a way, the probability of triplet formation is drastically reduced. So we thought that indeed, if we use this strategy, probably we should have molecules which are much more photostable. And really, this was checked for several molecules. Here I'm showing the decay of population of photoexcited molecules in different solvents. And there is a huge difference between alcohols, which form these complexes, and such solvents as hexane or acetonitrile, so both polar and non-polar. Anyway, the difference is again about 2 orders of magnitude. So one can enhance photostability in such a way. And then the third strategy we are currently probing is somewhat different because this is now the case in which we cannot avoid formation of the triplet. So the triplet is formed, and it is usually formed with a very high probability, like 80% in the case of porphyrins. So we thought perhaps we could at least shorten the lifetime of this triplet by quenching it by a certain substituent. This is this moiety here is cyclooctatetraene, and actually it has a very low lying triplet. It's very low lying in such a way that it cannot generate singlet oxygen, which is another way of protecting our molecules. And we are quite hopeful that using this strategy will lead to a great improvement in photostability. But until now, we had mixed success. In case of porphyrins that contain zinc, we really improved the photostability by at least an order of magnitude. But it turned out that if instead of a metal here, we have two protons, the situation is opposite. We actually deteriorate the photostability. Unfortunately, we have introduced another channel of the activation, which can lead to photodestruction, which is electron transfer. And we sort of knew that it was possible, but well, we tried. And as I said, the results here are mixed. So anyway, to sum up this part of my talk, there are various strategies of enhancing photostability, but still there's really room for improvement. And now let me switch to what I consider the main subject of our single molecule studies, which is investigation of porphyrin isomers. Over the years, we have been studying various porphyrin isomers. Porphyrin, by the way, is called pigment of life. It is responsible for the color of our blood, for the color of green or yellow leaves, and so on and so forth. But porphyrin is also a very good model for studying tautomerism. Tautomerism, which is a possibility of having these internal protons arranged like that, or like that, or like that, or like that, various tautomeric species. And these various tautomeric species are also quite interesting from the point of view of symmetry, because there's usually a double minimum or even a quadruple symmetrical minimum potential. And this potential, the barrier of this potential can be controlled by substituents on the perimeter. So we have a very well-defined geometry of a system with 2 intramolecular hydrogen bonds. And if we study the mechanisms of this proton transfer, we can really get quite interesting results and compare these results for various species of porphyrin isomers. In total, there exist 8 different porphyrin isomers, but only 5 have been synthesized so far. And we focus in our studies mostly on porphyrin and also on hemiporphyrin. Different symmetries, different possibilities of tautomeric forms, and different hydrogen bond strengths. If you look at the NH stretching frequencies, it tells you that the hydrogen bond is extremely weak here, extremely strong here, and more or less intermediate here. And this translates into completely different dynamics of tautomerism. I will be showing this in a second. So we are trying to understand the mechanisms of single or double hydrogen transfer reactions in these molecules. Various scenarios are possible. When it comes to cooperativity or lack of cooperativity, these protons can move stepwise, one after the other, or in a concerted way, synchronous or perhaps slightly asynchronous. Then we found, and I will show you this in a moment, that the tunneling cannot be neglected. Actually, this is a dominant mechanism, even at room temperature. And perhaps for physicists, it's not that strange, but for chemists, it's usually quite surprising. And then what is very interesting is the role of vibrational excitation. This proton transfer reaction cannot be decoupled from how the molecule is vibrating. Actually, this reaction path for proton transfer is a multi-dimensional reaction path, and one has to take into account several vibrations of the molecule in order to understand why the reaction occurs as it does. So in our experiments, we actually combined 3 different regimes. We started with kind of routine measurements of molecules in condensed phases, so liquids, gases, polymeric matrices. But then we are trying also to isolate our molecules from the outside world as efficiently as possible. So we do it by using supersonic jets or even helium nanodroplets. This we did in cooperation with Alvin Slenčka. Then we also do rare gas matrices, so low temperature spectroscopy. And these regimes for ensemble studies are combined with single molecule measurements. And the single molecule measurements are using fluorescence, Raman, or STM. And before I get into that, let me just summarize what we extracted from these ensemble measurements. And I owe a lot to Piotr Wita and Piotr Ciączka and also Piotr Kasprzycki. He was a PhD student of Czesław Radzewicz, and he actually constructed the setup for measuring the tautomerization rates in these porphyrins. And this is not trivial, because these two protons, after they are transferred, they actually lead to the structure which is not chemically identical, which is not chemically different from the initial one. This is the so-called self-exchange reaction or narcissistic reaction, in which the substrate and product are chemically identical. But of course, they are not identical spectroscopically, because the transition moment changes. It rotates by a certain angle. And this angle can be measured. It can be measured by stationary measurements, but it can also be measured by the time resolved studies, in which one excites with a linearly polarized laser pulse and then probes with another pulse, polarized parallel or orthogonal to the initial one. And by studying this transient evolution of transient absorption and isotropy, one can get rates. And actually, what is very nice is that in one experiment, depending on how you pump and probe, you can determine both the ground state rates and the excited state rates. So in one experiment, we are sort of killing 2 birds with one shot. And this has been done by Piotr and his co-workers for now, I think, more than 30 different molecules. And we clearly see that the rates are changing in a huge, well, they are changing by 4 orders of magnitude, depending on what we put on the periphery. so we are modifying slightly the average NN distance. And this slight modification of NN distance, which translates into modification of hydrogen bond strength, is leading to the change of tautomerization rate by 4 orders of magnitude. So the molecules which have the strongest hydrogen bond transfer this to protons in about 50 femtoseconds, and the molecules which have the weakest hydrogen bond need hundreds of picoseconds. Then we can also see that the rate in the excited state is about an order of magnitudes smaller than in the ground state. And this is because upon excitation, the molecule expands. It expands, and then the NN distance becomes larger, and the hydrogen bonding becomes weaker, and that leads to slowing down of the reaction. But such a behavior actually was already quite suggestive of tunneling as a possible contribution. And this actually has been checked again by Piotr by doing variable temperature studies, and you can see the characteristic shape of this curve, which indicates that at low temperature there's certainly tunneling occurring. The rate doesn't depend on temperature, or depends in a very weak way. But then we also have some kind of an activated process, and what is important is that this activation barrier, which is determined from this experiment, is much lower, several times lower than the calculated barrier. So actually what we observe is probably not the over the barrier crossing, but some kind of vibrationally induced tunneling. And this vibrationally induced tunneling, I will show you in a moment, is really the mechanism. So there are actually 3 channels responsible for tautomerization. We have the vibrational ground state, or the so-called deep tunneling, from the lowest unexcited vibrational level, and this is the only mechanism at very low temperatures. But then, as we raise the temperature, there's a possibility of activating certain vibrations which can promote this reaction. And actually, this activation energy determined from these experiments is actually coinciding exactly with the frequency of a very important low frequency mode. Of this mode, which, as you can see, is really changing the distance between nitrogen atoms. It's changing the angle between NHN. And so again, there is a constant modulation of hydrogen bond strength. How do we know this? Well, we know this from a completely different set of experiments, experiments in which we measured single vibronic level fluorescence in supersonic jets. And we observed that the vibronic lines are split. They are split into doublets. And these doublets are split by a different number depending on which vibration we excite. And actually, this is the vibration which has the largest splitting. The overtones exhibit even much larger splitting here. There are also vibrations which do not do anything. They actually exhibit the same splitting as the 0-0 transition. So we actually conclude that in this molecule, there are 3 different kinds of vibrations. The ones which promote tautomerism, they sort of lower the barrier for proton transfer. There are vibrations that obstruct this tautomerism, so they enhance the barrier. And the majority is neutral vibrations, which more or less retain the value that is for the tautomerism from the vibrationally not excited state. And actually, we can reproduce this data, this tunneling, splitting, and frequencies by solving a simple phenomenological Schrödinger equation, which assumes coupling between this low frequency mode and the high frequency mode, which is simulating in a way our tautomerization path. An interesting situation occurs when more than one low frequency mode gets simultaneously excited. Then, depending on which 2 modes we excite, we may really see the changes in the observed tunneling splittings. And again, of course, we know that the correct potential should be multidimensional. And when we use the 3D potential, we can reproduce the observed frequencies and splittings quite well by assuming certain parameters like reduced mass, the width of the barrier, so proton path, and so on and so forth. We can even try to see whether what we observe in the regime of coherent tunneling, which is supersonic jet spectroscopy, and incoherent tunneling, which is condensed phases, whether these two pieces of data are compatible. And they are quite nicely agreeing. For instance, from the tunneling splitting, we predict the rate of about, inverse of 2 picoseconds, and the experiment in condensed phases give us this. Then the squared ratio of the tunneling splitting is 7.4, and this in condensed phases we get 7. So this is actually working quite nicely. But then the summary of this, well, there are several conclusions, but I think what is the most important one is that tunneling is the dominant mechanism of tautomerization, even at room temperature. And tunneling should be quite sensitive to the environment. So if we can really modulate this symmetric double minimum potential, we may expect some interesting consequences in terms of alternating the rate of tautomers. And now, can we do this on a single molecule level? How do we study this proton transfer on the single molecule level? Well, we do this again using polarized light, but this time we are using either azimuthally polarized laser beam or radially polarized laser beam. And then we raster scan the sample. So this is like 2.5 times 2.5 microns squared. And this is experiment. This is experiment, and this is simulation, assuming a certain value of this angle between the two transition moments. And you can see sometimes a ring, sometimes a double lobe. What does it tell us? Well, a ring means that the molecule is really tautomerizing, because it then behaves like a dual dipole. Dual dipole should give us such a ring. This ring is not exactly symmetrical because this angle is not exactly 90 degrees. But anyway, once we see the ring, it tells us that we are looking at a molecule that tautomerizes. Once we see the double lobe, it's a little bit more complicated. It may mean that the tautomerization was stopped, but it may also mean that we are looking at a molecule which is differently oriented than this one. And actually we used this to determine the orientation in 3D of different molecules of porphyrin. By switching between this azimuthal and radial polarization, we can see how the image patterns change, and then we can tell with the accuracy of about 5 degrees how the molecule is oriented in space. So we can tell whether it lies flat on the surface or it stands up, or it can stand on both legs, transition moments, and it can stand just on one. Anyway, this tautomerism in such a way is a good tool for determining the orientation of a molecule. But we are more interested in the mechanism of tautomerization. And actually, this tautomerization can be dramatically slowed down in single molecules. We look at a single molecule that looks like a double lobe, and after some time, like 20 minutes, it starts tautomerizing. So the shape changes from a double lobe to ring, and then it changes to a double lobe again. But now the angle between the two axes of these double lobes is 72 degrees, and this is exactly the angle formed by the transition moment. So we know that we have slowed down the tautomerization from about 1 picosecond, this is what it takes in solution, to minutes, or sometimes even longer. And this was quite surprising. And we studied different molecules. At the beginning, we had bulky substituents on porphyrin, and we thought that it may be due to these bulky substituents. They may be differently oriented and so on and so forth. But then we studied porphyrin without any substituents here, and we get the same situation. We get a situation in which some percentage of molecules are tautomerizing fast, but other molecules are not tautomerizing, or they are changing their rate over time, over a macroscopic time on the order of seconds or minutes. Actually, we observed a very similar behavior for a completely different molecule for hemiporphyrin. It has 2 tautomers, and these 2 tautomers exhibit slightly different emissions. These different emissions can be detected. And then if you look at a single molecule for 10 seconds, one would expect that because the estimated tautomerization rate is of the order of, say, inverse microseconds, that we would always see the same spectrum, averaged over this 10 seconds. No, again, we found that there are molecules which sort of stop tautomerizing for much longer times. Well, this has led us to a model in which we are considering this tautomerization in terms of both intrinsic tautomerization coordinate in a really single isolated molecule and the environment. And the reorganization of the environment is really important because it can lead from a situation in which the protons are localized in one minimum to a situation in which they are delocalized. So from a non-symmetrical potential to a symmetrical, temporally symmetrical potential. And now we can understand why this tautomerism is so different in condensed phases and in solutions. Because in solutions, this reorganization coordinate, of course, corresponds to the motions of the environment that occur on the femtoseconds or perhaps single picosecond timescale. Whereas in polymers, this reorganization can take even minutes. And actually, the single molecule studies were nicely confirmed by the recent result of Piotr Fita and his co-workers. They found in the ensemble studies that at very low temperatures, the fraction of tautomerizing molecules falls to a few percent, whereas at room temperature, this is close to 100%. And again, this energy here that could be extracted from the Boltzmann distribution coincides with the low frequency peak in the Raman spectra of the polymer matrix. So this is the relaxation of the polymer matrix, which is really responsible for this intramolecular double hydrogen transfer. Now let me briefly turn to the other techniques. Time is running really fast. Raman spectroscopy. So we do it by creating hotspots in ensembles of gold or silver nanoparticles, and then we observe Raman spectra of single molecules, and they are very much different. The frequencies are always practically the same, but the intensities are completely different. These are just 5 different molecules, but if you just look at the story of one molecule, over time it may also fluctuate quite dramatically. When we do this, we actually mix 2 isotopomers. We mix 2 isotopomers, porphyrin, which has 12 deuterons on the periphery, and porphyrin, which is non-deuterated. Why do we do this? Because they have different Raman spectra, and then by doing the statistics, we know whether we are in a regime of single molecules or not. If we observe only spectra of one or the other, but not the mixed spectra, we know that we have achieved the single molecule regime. Actually, there's a surprise. By diluting, we see much more of the single Raman spectra from the undeuterated molecule than from the deuterated, and we can only explain this until now by assuming that the diffusion of our molecule in such an environment is different for deuterated and non-deuterated porphyrins. But what's important, we can also observe the changes in the Raman spectra. These changes we attribute to the trans-cis tautomerization events, which occur very, very rarely and only for a fraction of a second, and then the molecule returns to normal. But anyway, we can pinpoint this tautomerism by looking at the Raman spectra recorded in a fraction of a second. Actually, our time resolution is now 3 single molecule Raman spectra per second. And finally, we can now switch to microscopy, scanning probe microscopy. It took these people about half a year to learn how to separate porphyrins from other porphyrins, to really have one molecule of porphyrin lying on the surface. And then the first surprise was that the tautomeric form, which was most stable, switched from trans to cis. Actually, depending on what kind of metal one uses and what kind of surface one uses, one can stabilize or destabilize these tautomeric forms by up to 10 or even more kilocalories per mole, quite a large change. And then what they do, they place a tip above the molecule, somewhat sideways, and then they observe the current. And this current, of course, changes when the protons move from the left to the right and back. And by analyzing the time distribution between these events one can get the reaction rate. At 5 Kelvin, single molecule lying on a metal. And actually one can even do better than that. One can localize these protons by just shifting a single copper atom towards the molecule. By having this single atom close to the molecule, one can push the protons away from it, and then we have no tautomerism. Then using the tip, we are just shifting this single copper atom, and then the situation returns to normal, so to speak. Well, this is the animation that shows how it works. So this is a single molecule switch controlled by a single atom. The final slide. Recently, we found that by studying carefully this tautomerism in the molecules which have either 2 protons or 2 deuterons, or 1 deuteron and 1 proton inside this cavity, we can determine the rates. And then we found that the KHH rate is much larger than the rate which is observed when you have either 1 or 2 deuterons. And if you have 1 or 2 deuterons, the rates are comparable. And this tells us that at least lying on the surface, this molecule undergoes this tautomerism in a stepwise fashion. And a nice result was that once the protons migrate, the whole molecule is translated slightly along the surface. So actually the tunneling coordinate here requires including the translational degrees of freedom. So multi-dimensional process involving the whole molecule. These experiments actually have shown us that one can do tautomerization in a single molecule, not only by varying the temperature, raising the temperature, but one can use electrons, which are used in this microscopy. One can use light, which is actually absorbed by the support, by the metal. And then one can use even the mechanical force. We can now push the protons with the tip. So this is mechanochemistry on a single molecule level. Well, let me now summarize. There are a lot of conclusions. I think that the most important result is that by changing the environment, one can really slow down the reaction by many orders of magnitude. And this tells us that the rates of intramolecular processes can be controlled by the environment, so by intermolecular factors. Of course, tautomerization is a multi-dimensional process. And tunneling is extremely important, even at room temperature. We estimate that about 80% of the reaction channel is involved, deals with tunneling, perhaps even more. We simply cannot tell. And then what's so specific for single molecules? Such studies make it possible to observe molecules which have different potential energy profiles. But then we can look at a single molecule and see how these potential energy profiles change over time, or of course with orientation of the molecule, with the location of the molecules. Then these tautomeric forms can be really stabilized or destabilized by changing the environment. If we go to a metal, a completely different image emerges. And of course, one can use this as a tool for various applications. I was showing you this orientation, 3D orientation studies, but of course we can probe the polymer relaxation dynamics. We are actually doing it now. Or one can design the single molecule switches. And naturally, similar effects may be expected for other systems undergoing proton or hydrogen transfer. And just before concluding, let me just tell you what are our plans for the future. We are now entering the area of polaritonic chemistry, chemistry which is altered by placing a molecule in a nanocavity, or ensemble of molecules in a nanocavity. Well, in short, formation of polaritons, half light, half matter states leads to changes in energies, and these changes in energies may lead to changes in chemistry. And I don't have time to discuss that, but it seems that these changes would be mostly pronounced when you have a single molecule in a nanocavity. The challenge is, of course, observing a single molecule in the so-called strong coupling regime in such a cavity. Until now, only one paper has been published that claims that they did it, and we are trying to follow. And with this, I will conclude. Thank you very much.
Thank you very much for your very nice talk.